for a binary mixture in molar units, we can write the overall velocity of two components as the molar fraction of each component times each individual velocity and sum that up, right? So the overall velocity of the system equals to the sum of the velocity of each component times its own velocity. Okay? And so based on the definition above, this symbol here, the lowercase jay is the diffusion flux. The diffusional flux, so jay is equal to the overall concentration times the molar fraction of that species times VAY minus VY. So basically, you can think of the molar flux, the diffusional flux, is the flux of a particular species relative to the overall velocity. So it's the velocity difference of a particular species with respect to the overall velocity times its concentration. Okay. So again, the diffusional flux of B equals to C overall concentration times the molar fraction of B times V BY minus V, or VY, sorry, times VY. Okay, and as a homework, you would actually know that the diffusivity of species A and B will equal to the diffusivity of species B and A. Maybe we would do this as a homework assignment. Okay. So you will use the relationship here, this important relationship here, and these relationship here to get to the conclusion that the diffusivity of A and B equals to B and A in a binary mixture. Okay, so finally we can write our three-dimensional vector form of our Fick's first law. So 3D vector form of Fick's first law. We will have the diffusional flux of A would equal to negative rho DAB gradient of the mass fraction of A. B, or if we want to write this in the molar units, we use the capital J. A equals to negative DAB gradient of concentration A, and JB equals negative DBA, so we need to correct the previous one. So this is BA. Okay, so you can see again, the most important thing we want to introduce here first is the Fourier's law of heat conduction and Fick's first law, which describes the heat and mass flux as a function of the gradient of temperature or concentration throughout a particular length, okay? And they are related by the thermal conductivity and the diffusivity. Okay, so you can take a look at how these two are very similar mathematically. And we should also take a look at, compare the thermal conductivity and the diffusivity here. So let's take a look at that. So let's compare, So let's take a look, let's kind of compare these two. So compare the thermal conductivity and the diffusivity. So first, let's look at the units of these two specific coefficients. So thermal conductivity has a unit of watts per meter times Kelvin, or Kelvin is capital, Kelvin. And the diffusivity has a unit of meter square per second. Okay, so here we're going to introduce a concept called thermal diffusivity. So thermal diffusivity. And we use the symbol alpha. So alpha, the thermal diffusivity, is defined as the thermal conductivity divided by the heat capacity, the constant pressure heat capacity, times the density. And when you do that, you can figure that the unit now becomes also meter square over second. Okay, here the Cp is the constant pressure heat capacity. Per unit mass. Okay, and it has a unit of Joule per Kelvin per kilogram. Okay, and if we kind of, recall from fluid mechanics, so recall from fluid mechanics. Remember the kinematic viscosity. So kinematic viscosity, which we use a symbol of nu, equals to mu over rho, and also has a unit of meter square per second. So you can see that the diffusivity, the thermal diffusivity, and the kinematic viscosity all share the same units. Okay? And that's important because if they share the same units, that means they are they can become dimensionless groups. Okay? And dimensional groups are very important in our future discussions when we want to, quickly verify the relative contributions between momentum, between thermal, and between mass transport. Okay, and that gives us a very good way of simplifying our system in the future. So the important thing here is in the future, not necessarily now you're going to deal with it, but in the future we will be looking at these. Okay, so the important thing is that the ratio between the ratio between diffusivity, thermal diffusivity, and the kinematic viscosity, are all dimensionless groups. Okay, so for example, in the future you will learn the Prandtl number, or maybe you've learned it before. The Prandtl number, which we use PR to represent it, equals to the ratio between the kinematic viscosity over the thermal diffusivity. So it actually equals to Cp mu over the thermal conductivity. Okay, so it's basically already telling you, it's going to be indicating the relative ease of momentum and energy transport in flow systems. Indicate the relative ease of momentum and energy transport in flow systems. If the Prandtl number is large, that means the momentum transport dominates the energy transport. Okay? When the momentum, or when the Prandtl number is small, then it's the other way around. Okay? And this is going to be very useful if you want to, in the future you will know that if you want to determine whether, free convection is going to take place in a system or not. Okay? Now we can also introduce some other dimensionless groups. That's the ratio of these two, right? So you have also the Schmidt number. So Schmidt number, which we use a symbol of SC, equals to the ratio between the kinematic viscosity and the diffusivity. And then we also have the Lewis number, which is probably not as commonly used, but we can still introduce that anyways. The Lewis number equals to the ratio between the thermal diffusivity and the molar diffusivity. Okay, so basically they are describing the competing process in dimensional analysis. So they are basically, you can say they're measures of competing process in dimensional analysis. So don't worry about if you cannot catch up at the moment. We will come back to these concepts later on. Okay.